Hi and welcome to a discussion with Mudit Verma regarding hindsight priors for reward learning from human preferences. We're going to be focused on how to merge the topics of reinforcement learning with human preference input, and particularly how to design a system that's robust against the peculiarities that arise whenever you try to collect human preferences. I hope you enjoyed. I think a nice starting point for us would be to just give a high-level introduction of preference-based reinforcement learning, because
Right.
it's the first interview I'm doing specifically on that.
On
Could
PBR.
you just
Okay.
introduce the topic and what the background for this paper was?
So yeah, preference-based learning or PBRL, and nowadays I think an adaptation of that is RLHF, very popular in large language models. Any paper you pick on LLMs mostly would have some units of RLHF here and there. And the early roots of that is PBRL. And the main idea is that humans have certain kinds of preferences. I mean, it doesn't have to be humans, but it was built around that humans have some preferences, and then an RL agent or any kind of sequential decision making agent, right, wants to figure out what those preferences are. But it turns out, right, if those preferences are not symbolic in nature, right, if they are tacit, things like what is a good dance or what is a good way of swimming, there's no easy way to just say it out in an algorithm, right? You can't just list out step one, step two, step three. I mean, you can do some part of it. For example, if I'm trying to be a nice chef, I can list out a recipe, but that doesn't make me a nice chef, right? There are a lot of tacit elements that I'm just doing right because I have the skills. So how do you capture those things, right? It becomes very hard because people cannot express and you still want to learn it, right? So an agent still wants to learn it. And the idea there is that we can resort to some fundamental ways of learning what the human wants. And that is through some kind of a binary feedback. So that is, again, what RLHF is kind of building on as well. So the idea is humans, it's very hard for them to express what they want, but they can select, right? So even though you can't say what is a good dance, once you see it, you'll probably know that this is a good dance. Or even better, you can at least talk about it in a comparative sense, right? You can say, oh, this dance is better than this other dance, right? Even though the human has no clue how to dance, which is a related area called learning from demonstrations, even though the human has no idea how to specify in an algorithm or in RL what is called as a reward function for what a good dance would be, because they're not experts of dance, but they are more like a more like an audience, right? So in those cases, right, how do you capture those preferences? And the key idea is that you have these binary feedback expectations from the user to provide, and the agent's responsibility is to come up with questions or queries or pairs of behaviors that would be shown to the user, and the user gets to pick like A versus B and so on, right? And the whole idea is that given this kind of a data set that I prefer A over B, and like tons and tons of data set like this, I want to be able to learn some kind of a function which can now, it's just a predictor function, right? Given another new pair of A and B's, which one would the human prefer, right? So this is a standard machine learning, like binary classification objective, right? Now, given this kind of a binary classification objective, the idea is that we can maybe figure out, right, what are the rewards that the agent should use to drive its behavior. So we may have to get into a little bit of RL, which requires, the whole idea is that the agent is trying to interact with the environment and it receives some kinds of rewards from the environment or from somewhere, which indicates how good or bad the agent's behavior is. And ultimately, the agent tries to optimize over that, right? But in PBRL, that reward function is missing. In fact, that is given by the user, right? Through these thumbs up, thumbs down kind of a feedback. So the problem is that you have these pairs of A's and B's that is generated by the agent. The user is going to annotate which one they prefer more. And then you have to the agent has to convert this kind of a data set into a reward function, like something that slaps a number onto each and every state that effectively, some kind of an RL agent use to learn the behaviors, right? So the whole idea is how do you convert these up and down kind of feedback over the whole sequence into a reward value for each and every state. So that's, I think, most of the magic where magic lies. So the whole idea is that we could not give a number to each and every state because it's very hard. Nobody knows what is a good reward for a good dance. But once I have seen the entire dance, maybe I have some better idea of, I can just at least say like thumbs up, thumbs down, and then I let it be the agent's responsibility to convert those thumbs up and thumbs down into individual numbers along its behavior, right? So the agent has to figure out that, okay, the step 1 was good, step 2 was bad, step 3 was even worse, but step 5 was magically really good, and so on, just from those thumbs up and thumbs down, right? And so the first step is to learn this kind of a reward function, right?
So quick follow-up. Quick follow-up question on that. So do you have some more examples where that kind of feedback is the only viable approach? Because if we're talking about dancing, I think there are even TV shows about this where you have people coming on dancing and then you have like a board of judges or whatever. They give a number between 1 and 5 of how good the dance was. I feel like oftentimes that kind of rating is maybe easier even than comparing one to the other. Like giving a comparative number or a comparison between two different trajectories kind of presupposes that you're comparing apples to apples and not apples to oranges.
That's true.
Do you have some examples where really that kind of numbering of outcomes is not a possibility, and where something like this is the only viable alternative?
I think again, there are always better ways to improve PBRL, right? And in real world, you can do a mix and match between, okay, you do know how to cook something in terms of a recipe. It's just that you don't know how the knife has to move, right? Or what the motion of the knife should be, something like that. So typically, PBRL in its raw form is meant just for these tacit tasks, right? And the whole point is that it's very hard for people to even imagine what would be a good behavior, right? So they're basically pushing the responsibility of generating behaviors in their mind to the agent. So now the agent is figuring out how to bring apples and apples and query that to the user, right? And it is a fundamental challenge with PBRL that how do you make sure that those queries make sense, right? It is very possible that one behavior is very, very different from the other behavior, and the human has basically really no answer to that query, right? Like you can force them to just say thumbs up or thumbs down, in which case they'll have to pick something. But typically, the ways to get by that is you just add another option that they don't want to answer. So if it's apple to oranges, basically they get to choose not to answer. But that is just a waste of interactive query. Like you didn't really get anything out of it. And typically the ways to avoid it is those active learning methods where you figure out that's essentially what active learning field is for. You figure out what queries to make so that we can learn as much as possible. And in terms of examples, right, I would still resort to there are, for example, in this paper, there are several domains that we used, which is those robotics control domains of picking an object, moving things around, and so on. And those behaviors, right? I mean, it's very hard to provide motor control actions by a lay user, right? You can look at like a robotic arm and say that this motion looks good, this looks smooth, this is very risky, this isn't safe because the arm is just like flaying around or something like that. But if I start asking you in terms of, okay, does this angle of this motor at this point with this acceleration, does it look good to you? That kind of modality of interaction just doesn't work in robotics, right? So you have to find a midway. But I think in summary, I think your question was, is binary feedback the best modality? I don't think so. There
My
are
question was not so much on that. So I don't think you can always say which one is better,
right.
especially not in all circumstances. It was just whether you knew some application where providing a numeric input is not a viable alternative, because it seems like that should be the
Right.
default if you're
I
able
think,
to
yeah,
provide it.
I think I can say, right, what is a good essay, right? Providing a numeric input for a good essay is like very, very subjective. So anything subjective, I mean, your scale of 1 to 5 could be very, very different from my scale of 1 to 5. And if you want to actually scale anything PBRL or anything RLHF, in that case, there's this big problem, right? Like if you want to crowdsource this data, you can't. Binary
Mhm,
feedback you can crowdsource because A is better than B. Most of the people will agree, right?
mhm,
But your 4 on 5 and my 2 on 5 can be very, very different. And this is seen almost in paper reviewing, right? When multiple reviewers are actually trying to review a paper, somebody may really, really like the paper, but then only give a score of 3 to 5, 3 out of 5, and somebody who just doesn't like the paper but are more lenient, they'll give a score of out of 4 out of 5, right? So
mhm,
anything that is very, very subjective in nature, there's no there. Those kinds of cases you would want to rather resort to a binary feedback instead of just asking. I mean, even in those cases, having a number may actually help sometimes, but generally binary feedback is useful in those cases, right? And the
mhm,
other place, so first is subjective. The other place is when it is even hard for the human to imagine what would be the best case, right? So the whole premise of rating something out of 10 is that I know what a 10 could be, right? But if I have no idea what a 10 could be, for instance, right, let's say the agent is trying to solve a maze, right?
mhm,
The fact that it could solve it, I would say, looks good, right? But I have no clue what the optimal would be or how easy the optimal thing could have been, right?
mhm,
For instance, right, and I'll go back to my dance example now. Like I can rate comparatively what a dance would be better than some other dance, even though I have no knowledge of any kind of dance forms or I don't dance either as well. But if you just ask me to rate in an absolute sense a particular dance, it becomes very hard for non-experts or lay users, right? How would I even get about rating anything? So
mhm.
typically in those cases where there is a lack of inferential capabilities of the human, you would want to resort to binary feedback. But again, take this with a grain of salt because most of the actual real world use cases are hybrid approaches. So you don't want to resort to just one modality. You do want to take into account several modalities.
Okay. Can we talk briefly about the alignment of the implicit reward function? Because I take it you supply binary feedback to the model. The
Right,
model, in turn, through some mechanism,
right,
constructs an implicit reward function out of this, and you
right,
want it to be well aligned.
right.
Could you elaborate on that term a little bit?
Right. So there are two general ways of looking at alignment. The first one, which is more general version, is where robot has its own goals and own expectations and own like things that the robot has to make sure, right? And then there is alignment with the user. So it has to first make sure that whatever its own goals are, that's taken care of. And then along with that, the user is also happy every now and then, right? And then there is the spectrum. PBRL starts again from a more fundamental side where it is assumed that the robot has no life other than to support whatever the user's preferences are, right? So, one way of doing that is the human has to basically like their feedback is responsible for figuring out what the goal of the user of the robot should be, right? So if for instance, right, in this case, alignment is checked through the standard classification methodology, right? For instance, if the user has given me 10 different data points comparing A's and B's, and my reward function can do the prediction right? I can be a good binary classifier. So the way it works is you have certain behavior, which is a sequence of states. And for each state, I'm slapping a number onto it, which is the reward function, right? Which is giving the reward value for a particular state. Now, when we compare two behaviors or two trajectories, you just, like, one simple way of understanding is you just add up the rewards for a trajectory, for both of these trajectories, and then just compare which one has a better sum of rewards or return, as it is known in RL, right? So whichever has a higher sum is going to be the better trajectory in the human's mind, as we are approximating, right? So the whole idea is, how do you come up with these special numbers such that my prediction for a certain trajectory being better than other trajectory is consistent with the labels that I have obtained from the user, right? And the whole, like, idea of alignment, right? There are a lot of parts to it. There are subjective parts and objective parts. I'll maybe slightly cover some of the things. So we are simplifying the whole problem into, are we consistent with the labels that we have obtained from the users, right? And there is this kind of an assumption that if I haven't asked, then I cannot really comment on alignment. So it is very possible that I've only asked 2 queries and I'm consistent with those 2 queries, but the user had so much more to answer, right? So in which case I should extend my bank of queries that I've asked, right?
But that seems to be more of a, so help me understand where the line is between how you construct your feedback data set, let's say, and where actually model design comes into play here. Because it seems to me from just reading the paper that the alignment question is not merely one of asking the right questions, but also a matter of constructing a sound model. And I don't quite see where the problem is, or where the constraints on the model come into play, because it seems like we're inferring this output based on model. So let's say you have a set of scatter points and you try to approximate a line to that with mean square, like least mean squared error or whatever. The point will dictate what the line will be. And similar to that, you have some agent, and assuming you're using the inferred data set to construct a model, how is it that the model can be inappropriate for something like that? If you see my question.
That's a very, very good question. And that's, I think, yeah, you're on point, that is what this paper tries to kind of nudge towards. So the whole point is there are infinitely many ways to fit a certain points to any kind of, there are infinitely many models to fit a set of points, right? I just have to draw some kind of a curve so that it passes through these points, right? And the same thing happens with when we're trying to learn a reward function with these labels that we have, right? And that problem is called degeneracy of rewards. There are infinitely many ways, and so it is degenerate. And we kind of resort to what ML folks have resorted to solve that, which is the use of some kind of a regularizer or some kind of an auxiliary objective, right? So the only way to solve that, there are only 2 ways to solve it. Like, if anybody tells you otherwise, I should actually talk to them. The first one is you get more data, right? So more data is more data points, you get to have a better fit, right? Which is expensive, right? Because here it's you're asking a human in the loop, right? And that becomes very, very expensive. The second way in which you don't irritate the human is you have some kind of an inductive bias, right? So you make up your own beliefs that this is how a curve should look like, and we'll just follow that, right? And this is a very, like, popular thing, right? You have L2 regularizers when you're learning some kind of model. What is that? It's basically saying that, okay, something should look Gaussian or something should follow this kind of regularization strategy, even though there is no real mathematical reason to do that. There's more of a practical reason to do that, right? To force learning a model to improve generalization.
Okay.
The way,
So it seems to me that the alignment problem is very closely related to overfitting in general. That this problem kind of stems from overfitting.
Yes.
But is there more to it than that?
I think the one that I am mostly fascinated about with respect to alignment is, I think there is some name to this phenomenon, is people don't really know what their preferences are, right? And it is very hard, like, even if you ask some queries to them, right, they wouldn't know the impact of those answers when the agent is learning. And it is
Yeah.
only much later when the agent has learned something of useful nature, it is only then they would figure out, oh, no, this is not what I wanted, right?
Mhm.
So there are a lot of inferential limitations. So I think one answer would be that just collecting more data is not really enough, because people would miss out on a lot of things. So there is overfitting, right? Even if you have a lot of data, you can do really badly and there are ways to solve it and so on. But just having that amount of data doesn't really imply you would get a good preference model of the user. And that's where a lot of people are trying to use, let's say, large language models to capture some kind of common sense parts of what the user preferences would be and so on. In fact, there is very nice thread of papers by Russell who talks about that if you want preferences of a user, at the end you have to ask the users, right? There's no way, like there's no amount of inductive bias, guessing some kind of hypothesis space, using proxies like LLMs. No amount of all of that can help. Eventually you would have to ask the user if it is a very personalized preference that you're seeking. So I think there are those kinds of challenges. But with respect to PBRL and this paper, it was more about, okay, assuming collecting data is the way to go and people are all nice and we have all good humans who can answer things and they're very consistent about what their preferences are across the labeling procedure, can we reduce the interaction, right? And as I said, there are only two ways to reducing the improving the model. First is to collect more data, which essentially means I need more interaction. You can do some kind of data augmentation, which is one of my previous papers. You can do those kinds of tricks to just generate more data out of this set. But this way is more about, let's just not ask humans more, but let's just have some kind of, let's force the way we are learning the model to follow a certain way, and then let's see if empirically that holds, right? And this image is kind of what that idea talks about.
Right. So I want to jump into this in some more detail now as well, and we'll get to the auxiliary tasks, etc., in a while. But first of all, I just want to get a general overview of the
Right.
most important parts of this. So if you would mind breaking down just the general procedure of how this works.
Okay. So yeah, let me give like a 1 minute version of what this paper is trying to achieve, and then I can get to the parts, I guess. So, okay, think about when you're trying to state your preferences on a certain behavior, right? So let's take whether you like a movie snippet or not, right? And I've shown you this video, and your goal is to answer me whether you like it or not. Okay. Are you looking at each and every frame of that movie before you answer your question? Or do you look at it, make some kind of a summary in your head, and then come up with a preference label? Right. So typically the point is, as I would understand, not everyone would look at every single frame of a behavior that is shown to them. Right. So there are important parts in a behavior or a movie, and there are less important parts. Right. And this is called credit assignment, right? You are assigning some kind of a credit to parts that are more important, less important. So we take this idea that summaries is an important thing, right? People don't just look at each and every state, and they don't try to reward each and every state, just like, because an RL agent requires a reward for each and every state. But that's not how people work, right? They look at certain critical states in a behavior and then form their judgment based on those critical states. So that's the kind of, and it may not hold everywhere, right? If let's say it is another AI agent giving its own preferences, in that case, this doesn't hold, right? This is more of how humans work rather than how general preferences work, right? This is for just preferences of a human.
But just to add something to this, this is also generally how problem formulations are stipulated, even outside of the scope of this, right? So if you think about Atari game suites, which are popular for the RL space, your rewards or your payoffs from the environment are also discrete. You're not having a reward in the physical world in each frame, but rather you get accumulative rewards
Right.
if you do a lot of things well. Now, obviously, you propagate that to a reward function that gives a reward for
Right.
every state, but it's a secondary step.
Yes, yes, and slightly no. I think the reason why it is there in those RL works is because of just lack of effort, I would say, or I think there's limits of effort of what a reward engineer can put in. So I think there the reason why you don't have very dense rewards is because it's very hard to design those dense rewards, right? So it wasn't as if they were trying to give rewards to only few states, because in RL, dense reward is the way to go. The more nuanced, fine-grained rewards that you have, the better everything is going to work out. And typically in RL for Atari and RL for these kinds of domains where rewards are manually designed, it's very hard to do so. And there's in fact a lot of good papers by Anka on reward hacking, right? So where you try to over optimize, you're just like overzealous and you're rewarding every state, or you're figuring out a reward function such that there is some number for every state. In those cases, it's very likely that the final behavior, the learned behavior, may not be as good as what you would expect. Even though the final outcome here and in that case is the same, that you have sparse rewards, you have some kind of a summary or some subset of states which I'm looking for. There it is mostly because it's very hard to reward everything. Here it is because most of the states are actually useless, right? Especially in continuous control, where you're trying to have very smooth actions, such as picking an object, moving around, or even in this example on the left, there is Montezuma's Revenge, that Atari game. Most of the actions are not as useful. So I think there is this spectrum of, is it actually useless to reward every state, versus was I just lazy, or it's very hard to do that, right? So but here we take the stance that not every state is rewarding, and then if I can come up with some kind of a hypothesis of, okay, given a trajectory, what is important in this state, right? Like regardless of the task, right? So your task could have been anything, but given this kind of a movie snippet, what would you remember after 2 days, right? You could be asked any question, you just have to figure out some importance and that's very important because it's cyclic in nature. If I were to give you a task and then ask you what is important, that is what a reward function is, right? By definition of a reward function, it is trying to reward states which are useful for the task. So what we do here is, given some kind of a behavior or a trajectory, you have to figure out what would be a nice summary of that, right? What would be the states that are important in general, right? Like without just essentially specifying you the task. And we'll hold on to how we get there. But let's say we have something like that. Our idea is essentially to add a regularizer on top of our reward learning procedure. So whatever rewards that we're trying to learn should look like this, right? That's essentially inductive bias. Similarly, like for instance, in machine learning, in normal deep learning, you have these L2 norms because you want to have weights that are not as high of a number. And that's an inductive bias. That's a choice of the designer. So here our choice is, I am going to come up with this magical way of saying that certain states are important. And when you are learning your reward function for this specific task that the user has in mind, then try to focus more on these states rather than every single state, right? So that's, I think, the key thing that is going on here.
Okay. I think what would be interesting to dive deeper into in the beginning is the like attention mechanism here, how we determine which states are actually important. So conceptually, it's clear. We want to summarize this in some way, and some states we want to assign more credit to.
Right.
What is the effective technical approach? And here I'm really looking for kind of details on how you do this for assigning an important score to different states.
Right. So there could be several ways of figuring out what is important. And in fact, in some of the experiments, we just said, oh, everything is equally important, which is a uniform, there's no attention really. or it's everything is uniform, or there could be other ways of assigning importance. One of the things that actually worked out for us was we had this idea that if I have a video and I'm trying to predict the next frame, the final frame after the video is done, so the t+1th frame, in doing so, what are the states this predictor is going to look at when it is trying to predict the next state? So next state prediction is one of the things that we use to figure out the importance of individual states, right? And it's a mix of, in terms of motivation, right? You would see when you're training language models, you have this thing, right? Like, what were the important tokens which led to the prediction of a specific token? In videos, that's the same thing. You have, so there's a lot of correlation between importance in a sequence and next token prediction or next state prediction. So that's the task we take here. We take a transformer model because for sequences, transformers are really, really good. And they allow us to inspect attention, which is a known, still debatable, but a known way of inspecting interpretability of a model, right? So this notion of what is important, attention weights correlate well to that, right? There are other ways, there are gradient based methods and so on, but all we need to know is, given this sequence of states, what is important in doing this next state prediction? What we can do is we can learn what is called a world model, which exactly does this, right? A world model is supposed to take the history and try to predict what happens next, right? So it models the world. And the way to operationalize that is through a transformer, because transformer allows us, there has been instances where transformers are really good for learning a world model. A lot of papers have come out for that. Of course, LLMs are built on top of transformers, so that's kind of a world model in text to some extent. So those were some motivations as to why transformer. Now, when you're doing this, you already have a bunch of trajectories you can sample. The agent can wander around, so you already have a lot of data. So there's no limit to the data. You can just, the agent, so this step doesn't require human at all. The agent can just wander around and try to sample sequences and the next state as the label, right? Now what we do is we take the complete sequence and we'll throw it to the transformer, just like how you would throw in a sentence to a transformer, right? Mm-hmm. So if I remember correctly, it's encoder decoder model, if I'm not wrong. I'll have to look at the exact details somewhere in the appendix to figure out. But the whole idea is you throw in, just like in an encoder decoder model, how you throw in a set of tokens, you throw in the sequence, and then you want to predict this next state. Now, when that prediction happens, you'll take a look at the last layer or the penultimate layer of this prediction, right? So this transformer model would have several transformer blocks, right? So you'll take up what is the attention or the self-attention part of each of those transformer blocks. And there are ways to combine them. So essentially what is happening is, I just needed one attention map, which says this state is important over this other state, right? Since there are several transformer blocks, I'm getting several attention maps. So I need a way to aggregate those several attention maps into a single one, because in the end, I just need one assignment. I cannot have multiple, right? Mm-hmm. And there are ways to do that. The one I think we went ahead with is you just take the mean of across every layer. You just take the mean of whatever the attention map is, and then renormalize so everything is all like sums up to one and everything, right? Mm-hmm. So that is the way of getting this attention map here.
Mm-hmm. Okay, right. That makes sense. What is the parallel route through the model intended to do? So we have this reward model here that feeds into, or well, that's combined in this mean squared error here to the attention part. Could you elaborate on that bottom half?
For sure. So, okay, coming back to, we should realize how the data was collected, right? So the data, the human's comment was on the entire trajectory, right? So the human said thumbs up to the entire behavior, not to a specific state, not to a set of states, but the entire behavior, right? So there is some belief that we can put that the sum of the rewards or the net return that we get, or what a predictor is predicting, is more reliable than the constituent reward predictions. So the R psi naught and R psi 1, R hat psi naught, R hat psi 1, in the diagram. I don't think you can see my cursor, but where I've written reward prediction in that block. So those are the constituent rewards. The sum of those rewards, I believe, is a more reliable measure of whether the human likes this trajectory or not, right?
More reliable compared to the actual human input, or sorry?
More reliable to the way that I have divided that net G into these R0, R1s, and so on. So the sum is more reliable, but the way I'm distilling that sum or distributing that sum into these individual states, that I'm not, that's the part where it is degenerate, right? I could have infinite assignments in which I split this G for each and every state. So there is no real reason why this particular assignment should be the way to go, right? Whatever the model learned could have been good, could have been bad, and so on. And that's the place where we want to inject our bias, right? Because through the attention maps, we have already calculated what would be a reasonable, like what is a more important state and what is a less important state, right? So the distribution strategy we have already computed through the attention map. So we don't need the one that is already learned. So the R psi naught, R hat psi naught, R hat psi 1, and all those individual rewards are not useful. The thing that is useful is the net, the sum of those rewards. So we keep the G, and then we have this mean squared error to make sure that this G is split like the attention maps. So that is where you see the G alpha naught, G alpha 1, and so on, right? Because alpha naught, alpha 1, and so on is basically like a mass probability mass function, because it sums up to 1. And we are splitting this G across each and every, just like alpha, right? And then we have this mean squared error to make sure that our reward function is predicting rewards like the G alpha. So G alpha I, right? So this Ri should have been G alpha I, and that's where the mean squared error comes in.
Okay. So to summarize then, what you're doing in principle is to take the cumulative rewards that you get from a certain set of states, you split that reward up as a weighted sum, more or less, into states that where the importance or the importance of the state is the weight that you use in the allocation, more or less.
Right, exactly. And we do this for sequences. So instead of sampling like one state or something, we are just doing, so the whole trajectory together makes sense. We couldn't have sampled a single state and done this, right? So you have to sample a trajectory, then take a look at how good this trajectory or how bad this trajectory is based on the sum of the rewards that we are predicting, because we are anyways minimizing the cross entropy, right? So we are anyways doing good on the sum part of it. The thing that we're not doing good, or there is no real reason to believe we could do good, is how this G is allocated to each individual state. And that's where this attention map business comes in, because that gives us some kind of a bias to inject here. So that's why it's called hindsight prior. So once I have completed that trajectory, in hindsight, this should have been my allocation of constituent rewards. Right.
Do you have a criticism from your perspective of this approach? So it seems it seems to be a reasonable allocation strategy to look at the importance of the states and allocate thereafter. But do you have ideas where this might break, or criticisms of that approach?
I think one of the biggest ways it can break is when this attention map does not align with how really the reward should be split, right? For instance, right, the basis of what we're doing is on the assumption that next state prediction is somehow correlated to what the user preferences are in their mind, right? So the fact that I'm predicting next state gives me more or less some of the states that are at least important in the human's head. It is very likely that the human is a cuckoo human and they're thinking in a very different way. And they feel that entirely different sets of states are important, right? And in that case, I think it is more of a challenge of modeling the discrepancy between what the state is for the agent and what the state is for the human. And this strategy will not really work. But I think as far as redistribution goes, I think it's a very nice idea. It was presented before in a paper called Rudder, which was reward redistribution. And we applied it for our PBRL approach. And I think that idea is pretty general. You can apply it without really thinking a lot about whether it will work or not, because it's just an inductive bias. I think the problem would come in when the assumptions of whether this inductive bias is useful breaks, right? And for instance, right, in our case, if let's say it's a maze-like environment and the robot can just transport from one place to other, like magically go from one place to other, like there's no smooth trajectory, right? So it's just popping somewhere and then popping from somewhere else, just like those hamster games, right, where the hamster can come in from anywhere, right? In those cases, right, it's very hard to really do next state prediction, and it's very hard because it's pretty much random, right, what those states, the subsequent states are. And in those cases, attention weights would not really mean anything, right? And so that is why we took up these kinds of tasks where there is, somewhat of a smooth motion. Certain parts of the motion are important, certain parts of the motion are pretty much repetitive and not so important, and so on. But if the states are pretty much random, and in that case, this kind of an automated way of getting what is important doesn't really work.
Let's say I like the maze example, so if we stick to that, let's say we have a kind of maze environment, and it would be in an environment like that, if you're trying to solve the maze with as little of a search path as possible, assuming that you take some path to the maze and then you can reverse if the path is not good, and so on. It would be very easy to quantify which path is better than another one. So in some sense, it's very well a problem very well suited for this kind of approach. It's also nice because it's you take out some of the human element. It's quantifiable which of the paths are better than another. Even if you do randomize where you start in this maze, depending on which state you're trying to predict. So you could say that the state you're trying to predict is the state that contains the information of how far you traversed at the finish time of one of these ones. You could still compare in an accurate way two different trajectories. Now, with all of that preempting out of the way, what I'm trying to ask is, in a scenario like that, where it's kind of algorithmic in a way, you cut out the pathologies that arise with introducing a human in the loop. Do you still see that this could break somehow? Or I'm trying to pick apart the attention weight aspect of this in the, theoretical sense, not so much in the application where a human can give incredible feedback or something like that.
I think while you were saying, I could think of one definite way of where it will break. So while I'm saying this, I'll try to think of the answer to your question. I think one of the things that we cannot model is reachability. For instance, let's say there are certain states that the agent was never able to reach during the exploration. Let's say there is some key that is required to open a door and the agent never got to the key, so it really doesn't know what is outside of a room, right? But those trajectories can come later, right? So it's not right now, but it can come later. In those cases, right, this attention weight is just bogus. It doesn't mean anything because it was never trained on those kinds of sequences, right? In those cases, I think this method can break. But even there are some ways we can still save it. And that is pretty much the fact that we are banking on a large set of data. So our assumption in that case would be that those cases where we have unreachable states are rare. But if it is a commonplace, then probably this can break. But coming back to what you were asking, when we have good estimates of, there's, for instance, like we are in a maze and we are moving around, in those cases, I feel this will still work. I think the only point it will not work is, let's say you're moving in a maze and you magically transport from one state, like you just keep walking and then you magically transport from one place to the other, and that's pretty much random, right? So you could transport to, let's say, 4 places, and you keep transporting to one of those 4 every time. That the reason why this breaks there is because it's very hard to model what is going to happen next, right? Because you're transporting like randomly to anywhere, in which case that point where you transport is important, but where you'll end up going is pretty much unknown, and that will hamper the learning of the world model, right? So pretty much wherever a world model is hard to learn, which can happen when the transition dynamics are uniform. So for instance, like poker, right? Anything can happen because everything is pretty much uniform, and there could be other domains where the dynamics are uh, not really fixed. Like for instance, like here, if I move left, I'm pretty much going to go left. Even if it is a stochastic environment, a higher likelihood is that I'm going to go left. But if I take a left and I end up anywhere, in those cases, very hard to do, like learn a world model. And subsequently, it's very hard to get good estimates of these attention weights. And so it cascades around. So it's hard to learn a world model, it's hard to learn a good estimates of attention map, and then finally it's very hard to suggest that this attention map correlates to what the human has in mind, right? So there are 3 orders of things that will just cascade down and go really bad. So I think those are the places where it will break.
Mm-hmm. Right. Okay, very good. I want to talk briefly about the results as well. Given that we won't have time to go through all the figures, I'm wondering if there's something you think is particularly relevant to discuss in the results.
I think, I'm not sure if it's somewhere in the main paper, but one of the things I really liked was results on robustness. Right. I keep saying this thing that having an inductive bias is useful, right? So this is the plot where we really see why that is useful. So what happens is prior is our work, and Pebble is a baseline that we have. And if you see, right, and there are different shades of purple, this is the best kind of visualization that we could do. Happy to take any suggestions if to improve this, but generally you would see all these red curves are much higher than these purple curves, and the different shades of the same color indicates what is the percentage of noise that's there when users are labeling. So 40% of the time user wanted to say thumbs up, but they said thumbs down, and it's randomly injected. Now, in those cases, our method, the stuff in red, is still very, very robust, right? Up to around 20 to 40%. And that's pretty good. The reason why that happens, and that's probably why I'm like more interested in that direction, is because we are forcing or we are anchoring the reward learning to some kind of a hypothesis. So we made up this whole fluff about, okay, there is this kind of attention map. This is a reliable attention map. This is how rewards should look like. So even when there is noise in the labels, right, the agent has something to anchor onto, right? So it already has some estimate that it is getting from the attention maps. So even if the labels are incorrect, it doesn't have to resort to a random assignment of rewards. It has something to anchor on. In contrast, like these other methods or which doesn't use any kind of this anchoring strategy, there you can just keep like a pendulum, right? You can keep switching because you got some inconsistent labels, and then you have no way of knowing which, whether this reward that I'm assigning is a good reward or not, right? So I think generally I really liked this part of the work where we could be robust to noise because we have this inductive bias put in, and which is again a case in point as to why this method is a better generalizable method than other methods, right? Similarly, like I again keep giving the parallel to why L2 norm is better, is because even when you have noise, you can be slightly better than the baseline. And similarly here, when you have label noise, which is very, very which is a very big challenge when you are asking humans, because M-Turkers, you'll always have noise. Even if they are well-paid M-Turkers, they'll have some noise just because they're humans, right? So being able to take into account some kind of a noisy labeling strategy is very, very important, especially because as long as we are doing binary feedback, there is no other way for the human to actually say what they really mean, right? It's just the thumbs up, thumbs down. They couldn't have come in and said, oh, I feel, slightly more subjective about it. Oh, I don't really know whether it's a thumbs up or thumbs down. They can't do any of that. They have to pick a choice. In those cases, handling noise is very important. So I think this is the result I would say is, I think, a good takeaway from like why you would want to do a return redistribution as we do in this paper.
Mm-hmm. Just to make the comparison here more clear, if we're
Right.
talking about Pebble, do you have a view on what the assignment strategy, if any, is there? Is it, like you said, a uniform distribution of allocation to the
I
prior
think
states, or?
it's data driven. They don't force the model to any specific kind of distribution. I think I should have, uh, I think the plot on the right
Mm-hmm.
has different kind of redistribution strategies, but within prior or our work. With respect to Pebble, I think it's completely data driven. So there is no bias that they have injected. It's basically whatever amount of data you have, and we are trying to just learn a model by itself. And that's the main problem, right? It could resort to like the different seeds could resort to a different distribution strategy.
Okay. So then, but because they still run into the problem of having to take one reward and then allocate that to the prior states. And
Right.
are they doing that? So you have to pick some way of doing that, as we were talking about before,
So
and you
they
can
don't
choose.
pick. It's the model that is learning. Like, so it's completely data driven. So they don't pick that let's have the first state be
Mhm.
A units of importance. They don't do that.
Right.
Importance is implicitly learned through data.
Mhm. Okay. Okay. Good. I think as far as the results go, I don't know. We would still have time to look at one more figure if you think it's important. Maybe this one is another comparison of, I think, how large of a contextual window we have, right?
Yeah, I think that was very important. I think when we were working on this paper, one of the main challenges of learning a world model is it's very hard to have long context windows, right? So now the problem is much less of a concern. So remember those early days of LLMs where the
Mm-hmm.
context window would be just, I don't know, very, very little, and to
Yeah.
the extent that you can't really do much. That's the problem that was there way like long back. But I think the architecture, right? I think Transformer XL is the one that we use in this paper. That's the one that had this breakthrough that you can have longer context windows.
Mm-hmm.
So we wanted to push for that result, that even if you have longer trajectories and people are giving thumbs up and thumbs down on really long trajectories, this method can still work. Because remember, if it's a really long trajectory, then there are more critical states, and it's not just you have to pick one critical, right? If it's a very small window, then it's easier for the agent because it has to pick just one probably, right? But
Mm-hmm.
as the length increases, there are more number of critical points in the trajectory, and whether we are still able to capture those is shown through these results, right? If in fact, I think, yeah, as in the figure on the left, if you look at Pebble, which is the purple curve with
Mm-hmm.
200 steps in the trajectory, the performance doesn't really go like as great. Like it's much worse than our work in either case, right? So
Mm-hmm.
those baseline methods cannot really handle long trajectories, and the reason is, again, the way you split the reward or return for the entire trajectory is even worse when you have longer trajectories, right? Because you have to just again figure out how to split the number 10 into 100 different states versus 200 different states, right? So the problem keeps getting worse and worse. And since we in our work have this anchoring strategy, we have this anchor created by the attention map, we are much more robust and we are much more better in that regard.
As a follow-up question, how come we don't see a significant difference between the two context window sizes for Pebble? So we have one of 50 and one of 200, and they seem to
Right.
be pretty aligned in terms of performance.
Right.
Would we not expect the 200 one to significantly underperform compared to the 50?
Right. I think there is some kind of like reason to it. in general, like empirically, it did not happen. But I think it happens with some of the other baselines. So much of the works that are there, including Prior, builds on Pebble as a backbone. So you have the main Pebble, and along with it, you do some kind of tricks such as the ones in this paper to improve Pebble in some way, right?
Right.
So while Pebble is kind of robust here between the trajectory lengths, the other variants of Pebble, right? So there is, I think, like multiple papers that have come out that play around with what Pebble is trying to do. Those papers, right, are actually very, very sensitive to the context window length, right? So as the trajectory grows, they're not able to keep up. So I think I should have, in fact, included some of those results. But generally, Pebble is kind of okay with longer lengths, but extensions to Pebble don't really pan out as well. So it is important to actually do a quick check whether longer trajectories make sense.
Okay. Very good. I think this is a good place for us to stop talking about more material. I would round it off here, but before I do, I would just ask if there are any key conclusions from your side or any recommendations that you would give to the audience as a consequence of your investigations.
I think like one big takeaway that I think I've been trying to push throughout this conversation is that this idea of return redistribution and anchoring to some kind of a bias that one already has can be very, very helpful in bringing down the cost or interaction cost with the user. And more so for alignment, let's say in LLMs or these other large models, like you already have a lot of ways of saying what is good or not. You have like so many scientists and engineers working on that. So there are ways to already have these kind of biases set up. So you don't have to be completely driven by the labels given by the user. There are these kinds of biases, and this method is a case in point on how to use those biases when you're doing PBRL or when you're doing RLHF. So I think that's the main takeaway, that including these inductive biases should be the way to go. And end to end, just completely data driven, I don't think that, I mean, it will work, but it will be very, very inefficient for the humans around.
Okay, so, awesome. Then let's cut it here. Thank you very much for taking the time.
Of course. Yeah, this was a very fun. I think I'm talking about this paper after like some time, so it was very nice to catch up on some of the parts of it.